Gave a little quick introduction to 4.4 before. I want to start with the basis. The basis here is defined as a set of vectors. If they form a basis for a large space, a vector space, those vectors in that particular set must span the vector space, and those set of vectors must also be linearly independent. To show that a set of vectors form a basis, we have to show both of these two criteria. And to show that, we simply use the definition straightforward to show that a set of vectors in some set, capital S, forms a basis, that S spans V, and that S is also linearly independent. Let's look at a problem. Here, show that the following set forms a basis for R3. To show that this set forms a basis in R3, we must show that the set spans R3 in that the set is linearly independent. So first, to show that the set spans R3, we must show that any arbitrary vector in R3 can be written as a linear combination of the given vectors. Say here, say B that here this vector B can be written as a linear combination of the given vectors. So that is for these vectors here, so for 3, 1, -4, 2, 5, 6, and 1, 4, 8, there exists scalars K1, K2, and K3. K1 times 3, 1, -4 plus K2 times 2, 5, 6. I have to write them standing up so I can save my space. It's equal to that B1, B2, and B3. Well, here we say that thus by the monster theorem, it is sufficient or tantamount to show that the three vectors as a matrix can either be reduced to the identity, or that coefficient matrix, its determinant is not equal to 0, or that 3 by 3 coefficient matrix, the inverse exists. Either one you can pick, it doesn't matter, to show the equivalence. Goodness. Okay. Here, let's rewrite this. This implies that 3, 1, negative 4, 2, 5, 6, 1, 4, 8, B1, B2, and B3. By the monster theorem, it is sufficient to show that the matrix 3, 1, negative 4, 2, 5, 6, 1, 4, 8 determinant is not equal to 0. Because you remember in that monster theorem, or that equivalence theorem, it says that if the inverse exists, that is the same, it is equivalent to saying that the determinant is not equal to 0. That's equivalent to saying that the system AX equal to B is consistent, or that is, has a unique solution. We're trying to solve AX equal to B, but we don't know what B is, right? Because you get B1, B2, B3, they're arbitraries, any vector out in R3. So since that's difficult to show, because, to show that, you know what you have to do? You have to show every vector in R3. Pick them all out. How many vectors in R3? It's infinitely many, right? How many pebbles will it take to fill up this room? Infinitely many pebbles, right? How many points exist between the interval 0 to 1? Infinitely many. It's an infinite set, right? Cantor gave us that, and also Abel as well. So since it's difficult to solve this system, then we use the monster theorem and its equivalence to show that something that's a little bit easier to get is worthwhile. Okay. So here, did anybody get the determinant of this matrix? This determinant is not equal to 0. Okay? I use other equivalents. I reduced mine down to the identity matrix, and so I got it, and so that's fine. So here, this implies the given vectors span R3. Secondly, we must show that the given vectors are linearly independent. To do this, we say that there has to exist these scalars such that the linear combination of the scalars in those vectors equal to 0 has to imply that K1 equals to K2 equals to K3 equals to 0. Now, on a graphing calculator, we solve and that does imply that K1 equals to 0, K sub 2 equals to 0, K sub 3 equals to 0. What do you get? Actually, this system reduces to the identity. So, thus, the vectors are linearly independent, and therefore they span R3. Therefore, they form a basis for R3. Okay. Now, I give you one problem on the test like that, and this is the argument in terms of how you want to show that. You're going to show two things. Show that the vectors span the vector space. The same argument here. All I've done was just to mimic the definition for spanning. And then you must also show that the vectors are linearly independent. I've just mimicked the definition for linearly independence. Okay? Now, quite frankly, you can give the proof of this in either one or two sentences. Because all you have to do is just take the vectors, put them into a matrix, reduce the matrix to either the identity or the determinant, or find the inverse. If the inverse exists, if the determinant is not equal to 0, if the matrix reduces to the identity. If you have three vectors for the 3 space R3, then you can just take that one matrix, reduce it, get the identity, and say that these vectors form a basis for R3. You're done. And that's pretty cool that life is easy like that. I want you to show each step in detail here's the reason why. It's possible that I can switch that up. That is, that I can give you, say for example, 4 vectors for R3. And I can ask you to show that these vectors form a basis. Well, if I got 4 vectors in R3, then I know by a theorem they're going to be linearly dependent, but they may span. So you would have to still show me that if it fails, why does it fail? You know, and of those 2 criteria, you know, which one is indeed satisfied? And so it's possible that if you have the vector space R3, I can give you 2 vectors. It's possible that those 2 vectors may be linearly independent, but they would never span R3. Right? So I could really tweak it and change it up, throw you off, whereby you really would have to think then. But what I'm going to do is give you something very straightforward. I'm going to give you 3 vectors for R3. I want you to show me that they form a basis by mimicking this proof that I've just given right here. Yes, sir. Mm-hmm. Exactly. But it's possible that they can be linearly independent in R3. Yes, sir. Okay? So, just got to watch out. Now, I'm going to be very straightforward here with this test because I'm looking for great results. And I think I can help you out. Now, show here that the following polynomials form a basis for P3. Let me give them some names. It's called V sub 1. This 1 plus x. I'm going to denote it as 1, comma 1, comma 0, comma 0. V2 is 1 minus x. I'm going to denote it by 1, comma negative 1, 0, 0. V3 is 1 minus, look at that, this is 1 plus 0x minus x squared plus 0x to the third. I'm trying to show you all of that. So this is 1, 0, negative 1, 0. Then V sub 4 is 1 minus x to the third. So this is 1 plus 0x plus 0x squared minus x to the third. And we'll just say this is 1, 0, comma 0, 1, 0, 0, negative 1. Right? You see how we represent those polynomials by the vector form? Do this one, and then I work a problem on the coordinate basis, and then I'm finished with this section. Show that V1, V2, V3, and V4 form a basis for the space of polynomials of third degree. We must show that the vectors span P3 and that vectors are linearly independent. Okay. To show that the vectors span P3, we must be able to write any arbitrary polynomial in P3 let's give it a name, say b, which equals to b naught plus b sub 1 times x plus b sub 2 times x squared plus b sub 3 times x cubed as a linear combination of here of the given vectors. So what we have then is some k1 times v1, which is 1, 1, 0, 0, plus k2 times v2, which is 1, negative 1, 0, 0, plus k3 times v3, 1, 0, negative 1, 0, plus k4 times 1, 0, 0, negative 1, is equal to this polynomial b naught, b1, b sub 2, and b sub 3. This implies that the system that we get is 1, 1, 0, 0, 1, negative 1, 0, 0, 1, 0, negative 1, 0, 1, 0, 0, negative 1. Here, b naught, b1, b2, and b3. By the Monster theorem, it's sufficient to show. Let's see, what did I do? Equivalence. Here I'm going to see if this coefficient matrix reduces to the identity matrix. So here, no. By the Monster theorem, it's sufficient to show that the coefficient matrix reduces to the identity matrix. Well, if you take that coefficient matrix and try to reduce it on your graphing calculator, you get it. Okay. So thus, there by the Monster theorem, these vectors span P3. The neat thing about using that equivalence by looking at reducing to the identity matrix is that that also kind of sets up for linearly independence as well. And so I'm going to piggyback on that and just say that, and then you can get the second part, and these vectors form a basis. Yes, sir. Yeah, by stating the monster theorem or the equivalence theorem, by that theorem we can show equivalence, that instead of trying to solve ax equal to b, all we have to do now is to show that the coefficient matrix can be reduced to the identity matrix. And you can pick whichever equivalent part you want, it doesn't matter, because they're all equivalent. So if you want to show that the coefficient matrix reduces, that its identity, that its determinant is not equal to 0, you can say that, Or if you want to say that I can take the coefficient matrix and see if I can find the inverse. On your graphing calculator, just type in this matrix, inverse. Does the inverse exist? Hey, that's equivalent to saying that ax equal to b is consistent, that is unique, that is, it has a solution. So yes, sir. So here we say also from above, the vectors are linearly independent. That is K1 times 1, 1, 0, 0 plus K2 times 1, negative 1, 0, 0 plus K3 times 1, 0, negative 1, 0 plus K4 times 1, 0, 0, negative 1 equals to 0 implies that K1 is 0, K2 is 0, K3 is 0, K4 is 0. Now, how do I get that? I get that by reducing the matrix to its identity form. That's why I said from above. Notice here, if you take this identity matrix, set it equal to 0, you get K1 equal to 0, K2 equal to 0, K3 equal to 0, K4 equal to 0. Right? So we kind of did, 2 and 1 there. So also from above, the vectors are linearly independent. Therefore, the vectors, all polynomials here, they're all polynomials, but we've written them in vector form. The vectors form a basis for P3. Okay? And the rest of them go in that order. Show that these do not form a basis. When you go through the steps, you'll see why. Coordinate basis. I'm just going to do one of these, very straightforward. We say that a set S, if that set S is a basis for a vector space, that is that this set capital S, it spans the vector space, those vectors are also linearly independent. So if I'm given that, that's good. And we say let V be a vector expressed as a linear combination of the vectors in S. That is that V can be written as C sub 1 times V sub 1 plus and so on, C sub n times V sub n. It should be V sub n. So we call the scalars that we get from the linear combination, we call the scalars the coordinates relative to the basis S. Thus, the coordinate vector of V relative to the basis S is denoted here. And so if a question asks you to find the coordinate vector relative to some basis, all they're saying is solve the system, and the system solution that you get, those are the coordinates. That's all. Let me write it out so you can see it. So here, find the coordinate vector relative I thought I had corrected this. Find the coordinate vector of V relative to the basis. That's better notation. So find the coordinate vector of V relative to the basis here that's given. And so all they want you to do is this, is to set up C sub 1 times V sub 1 plus C sub 2 times V sub 2 plus C sub 3 times V sub 3 is equal to V. And once you do that, basically you're solving for C. Solve for C sub 1, C sub 2, and C sub 3. So here's what we have. We have C sub 1 times V sub 1. That's 1, 0, 0. Plus C sub 2 times V sub 2, 2, 2, 0. Plus C sub 3 times V sub 3, 3, 3, 3. That's equal to V, 2, negative 1, 3. So basically, what are the components of V, of the vector V, formed by the linear combination of the given bases, V1, V2, and V3? In other words, simply just solve the system. And when you solve the system, the values you get will be C sub 1, C sub 2, and C sub 3. Let's see. Just some fancy phrase, coordinate vector V relative to some basis, just some fancy phrase of just saying solve the system. Look, so I say here, that is 1, 0, 0, 2, 2, 0, 3, 3, 3, here, slash 2, negative 1, 3. This implies that when you solve it, you get 1, 0, 0, 0, 1, 0, 0, 0, 1. Three, negative 2, 1. 3, negative 2, 1. So the coordinate vector of V relative to the basis S is equal to the C sub 1, comma, C sub 2, comma, C sub 3. See, that's how it's written there, which is equal to 3, negative 2, 1. In layman's terms, solve the system. Any questions? That's it, very straightforward. Okay? So it's just two things in this section. Given a set of vectors, can you show that those vectors form a basis for a vector space? Two things you're going to show: that these vectors span the vector space, and that those vectors are linearly independent. The next question on the test would be find a coordinate vector relative to the given basis. So they'll give you maybe some vector v, and then they give you some vectors for a basis. All they're saying is they're taking the definition for the spanning set, a set that is set to span a vector space. They say, given some arbitrary vector in that space, can you write that vector as a linear combination of the given vectors? Right? Here they're already claiming that that vector out in space, the arbitrary vector, is actually the vector v. Right? That's what it is. They're saying that this vector v, let v be some vector in capital V, in the vector space. Can v be written as a linear combination of the given vectors? If so, what are the components of that vector v? What are those components or those coordinates? So here we say that that's simply saying that once you set up v as a linear combination of v1, v2, and v3, what are those scalars that produce that? What is c1, c2, and c3? Again, in other words, just solve the system. And when you solve the system, those values you get will be those coordinate vectors relative to the basis. Okay. Any questions? Let's look at the